All right, we're waiting for it. We're waiting for it. I'm watching the clock. I'm watching the clock. It's a long minute. It's a long 30 seconds. It's like watching the grass grow. Come on, time. You can do it. Yay, there we go. All right, it is 2 hours UTC, and it's time again for Astronomy Daily Live. So, hey, everybody. Nice to see you. Come on in. Come on in. Join the ever-growing circle of friends who come together pretty much every single day, same time, same place. Turn off the TV, forget about the news, and just think about and share this passion for all things astronomical. So come on in, friends. Nice to see you all there. I'm going to pop over to the chat here really quick and just see Uncle Bill is there. Atta, hey, nice to see you there in the chat. And on the panel again, Bobby, hey, how's everything over there?
Nothing much except we're being punished, but we're being punished by that solar wind, and it's causing a lot of stuff with radio propagation.
Your audio is really breaking up in a funky way. We kind of got robot Bobby there for a second. It's that Bluetooth. That one. It's the Bluetooth.
No, my Bluetooth speakers has eventually died, and I'm using my Tabito B115 because on USB mode I can have audio and recording up on it and stuff. So that's so yeah.
Okay, well, cool. Yeah, I guess there's a coronal hole that's sort of spewing out a shower of stuff, and yeah, that tends to wreak some havoc on the Earth's magnetosphere and also, of course, the ionosphere. And when the ionosphere gets messed around with radio propagation, for some goes good and for some goes bad. So yeah, very cool. Yeah, solar wind. So I've got I definitely have the hydrogen hydroxide tonight, HOH. So cheers.
Oh, Becky.
And I'm going to start up my smartphone so I can sort of monitor the live stream here. That's always fun. And I'm going to mute that. Here we go. Okay, so that is muted. I'm gonna knock Bobby out here. There we go. All right. Well, cool. Well, welcome everybody. Come on in. Yeah, I guess just a couple of things before I get started. Uncle Bill, thanks for the link to Space Amanda. To Space Amanda. I'll have to watch / listen to her a little bit more. But yeah, sounds like she knows her stuff and pretty enthusiastic. She was trying to show the moon tonight. She's got a 10-inch Dobsonian of some sort, and she was trying to look at the moon tonight, and it was cloudy at her location as well. I'm gonna share my screen here. I'll hide that, and so there's sort of a link to her thing. In fact, what I'll do is I'll just grab that and put it in the chat as well. So everybody can have access to her. Always happy to promote other astronomical slash space slash science shows. So Uncle Bill's been waiting weeks to catch a scope stream. So okay, yeah, she's mostly into gaming. So yeah, you know, I think Twitch, that is sort of the format for Twitch, right? It's mainly a gaming platform, but there are, you know, quite a few science streams over there, and I see no reason why, you know, there shouldn't be. So, Bobby, I'm going to go ahead and mute you. Here we go. Okay. So I was looking sort of for a little while today to find a light curve of that Algol type star, Delta Librae, and I finally found a paper that actually had a light curve in it. So there it is. There it is. This is a eclipsing binary system, and it just so happens that the secondary star actually passes in front of the primary star, and that's why you see this dimming event, and it drops by about a magnitude or so, right? Actually, I think the period here is something like 2.5 days. So from here to here is 2.5 days, and from sort of the beginning of the eclipse to the end of the eclipse, we'll have to look and see. But yeah, you know, that's just a few hours, right? But yeah, nice clean thing. You notice that there's a dip here too, and that is when the secondary star is actually behind the primary star. You actually get a dimming event there too, because, you know, just sort of the opposite, right? The primary is blocking the light from the secondary. See, here and here, you're seeing light from both of the stars, right? But here, you're seeing the light mainly from the primary and not so much from the secondary. And here, you're seeing light mostly from the secondary and not from the primary. So obviously the primary is brighter than the secondary, hence the names, but that's why you sort of see a double dip here. And you know, the depth of this can tell us things about the inclination of that orbit, and I think maybe also like the eccentricity of the orbit, how much of a ellipse it actually is as the secondary orbits the primary. So yeah, you know, there's actually a lot of information in these light curves. You know, how fast this dips, sort of the shape of this curve. You know, also how long it takes. You know, can tell you things about the orbital periods. I'm sort of thinking too that you might be able to figure out make a guess as to at least the relative sizes of these two stars. So yeah, lots of information in these light curves. So, but yeah, you know, found one sort of some older data, but definitely some pretty good data there for sure. So yeah, that was Delta Librae. That we were sort of looking at yesterday, and I wanted to follow up on that a little bit more. And actually, I want to follow up with the constellation of Libra a little bit more. Look at a few more of the objects in there, maybe play with some pictures and whatnot. But before I do that, I'm going to check my chat again. Hey there, Sorcerer X. Nice to see you there. I think we just met over at Space Amanda's Twitch stream. Is that correct? Yeah? Okay, cool. I think so. So yes, welcome to the universe. And actually, as Uncle Bill calls it, he calls this the lettuce bin. So yeah, we are in the lettuce bin. So welcome. So this is just a fun, casual get together of friends every single day. It's like a circle of friends. We're sitting out on the porch in our lounge chairs, which are with our consumables of choice, and we're just sitting around talking astronomy for about an hour or so, pretty much every single day, same time, same place. So before we get back to the constellation of Libra, though, I wanted to talk a little bit about a really nice binary star called Alberio. Now, those of you that have a telescope, I strongly encourage you, and here I'm gonna get back over here. I'm gonna stop sharing my screen. There we go. So those of you who have a scope, I strongly encourage you to take a look at the visual binary star called Alberio, Alberio. It's in the constellation of Cygnus, and it is up right now. Yeah, I mean, pretty much as soon as the sun sets, it's up. It's going to be up over in the east or so. Pull up Stellarium or pull out your charts to find out exactly where it is. But it's an absolutely stunning binary star. I'm not going to give too much away. I want you to actually see it to kind of appreciate it. But what is stunning about it is the colors of the stars, and actually to really get the best effect, to see those colors best, it's actually best to find it, get it into field of view, right, and then change your focus, defocus, blur the stars a little bit. That'll spread the light out a little bit and actually bring the colors out a lot more. And it's absolutely stunning. It's absolutely fantastic. So check out Alberio. And the reason why I bring Alberio up is not only because you should be looking at this thing, because it's absolutely fantastic, but up until recently, it was thought to be like an actual binary star, right? One star sort of going around the other one. And the recent GAIA data release 2 data shows that it looks like it actually isn't a true binary system. One star is here, and one star is way behind it, and that can be measured through this technique called parallax, which we've talked about before here. So what I did, I sort of wanted to look at this. It's like, okay, well, let's see what they are talking about, right? So I'm gonna share my screen again, and I'll show you some plots. I'll show you some plots that I can make here. This is sort of this is astronomy on the fly. Yeah, there was a little bit of feedback, Bobby. So yeah, no worries. When you want to chime in, unmute yourself. Feel free. No problem. No problem. So contemplating the cosmic garden. Ah, I like that much better, Uncle Bill. I think this should be the cosmic garden. No, this is not the double-double. This is another one. The double-double you're talking about, probably the system up in Lyra. Epsilon, I believe, is the double-double. So let's see. Okay, so let's go over here. I've already made some plots, but let me go back here. I'm using GNU plot to do this, and I think, let's see.
It's not Bluetooth, but USB. I'm using USB now because of my Bluetooth. My Bluetooth speaker's got a bad charging port.
Bobby, you were robot voice for most of that.
Yeah, I think the Toledo B115 is not the greatest when it comes to computer mode.
I see. Gotcha. Okay, so here.
But when I get my check again, I'm going to get another Bluetooth speaker with a nice decent microphone, and we'll try from there.
Cool. Cool. Ain't technology great? So I've already gone over to GAIA and actually grabbed the data I wanted. And here is sort of an example of that, right? This is just a big, huge text file, and each field is separated by commas, right? So this is some kind of identification number. This is the right ascension, the declination. I think this is the parallax. This is the proper motion in right ascension, the proper motion in declination, and then the visual magnitude, right? And I've sorted these by magnitude. So the brightest stars first, and then the second and the third, and on and on and on. So with GNU plot, I can just, as you can see here, what I'm going to do first is I'm going to plot RA and DEC, right? And then I'm going to make the size of each dot correspond to the magnitude. So a bigger dot is going to be a brighter star. So let's do that first. So I want to look at column 1, 2, and 3. So I'm going to change this to 2, 2, and a 3. And then my magnitude is column 1, 2, 3, 4, 5, 6, 7. And I'm going to do, see that, minus 7. And I think that should do it. Point type is 7, which is a circle. Color is an 8. And then the point size is going to be a variable, which is this equation here. So I'm just taking column 7, and I'm subtracting it from 17, and then I'm multiplying it by 0.25 to give a point size. Let's see what that looks like. Okay, there we go. So there's Alberio, and it is definitely a visual binary star. I'm going to change those sizes a little bit. Let's just knock this down. a little bit like that. Okay. So there's Alberio, right? Binary star. And so the bigger the dot, the brighter the star. That's how these things go. So obviously, these two guys are really, really bright. And then we got a bunch of faint stars around there. There's an interesting line of stars here too. That's kind of cool. Okay. And then actually, let me order this correctly. The right ascension needs to go in the other way around. So let's go 292.8 to 292.55. Okay, so that's what it actually would look like in the sky. See, so this is north, this is south, this is east, and this is west. All right? So that's what it actually looked like in the sky. So yeah. So now what we can do is we can actually look at this in a couple of different ways. And as I said, the thing that sort of prompted me to want to look at this was that, for years and years and years, we thought that this was a true binary star, that this star, sort of the secondary star, was going around the primary star in some kind of an orbit, right? I mean, it doesn't have to be a circular one or anything, just some kind of an orbit. And the news is that they probably aren't associated with one another at all. One is in front of the other relative to us. And the best way to see that is to actually use the parallax values here. So as you can see, those two parallax values are different, right? The units here are actually milliarc seconds. So this first one, which is the brightest one, it has a parallax of almost 10 milliarc seconds, where this one has a parallax of about 8.3. So what that implies, right, is that this one, the brightest one, is actually closer to us than the fainter one here. So let's just plot that. So let's do, instead of showing the size of the dot being the brightness or the magnitude of these stars, let's make the size of these stars the parallax instead. See, so a big dot will therefore be a large parallax, and a smaller dot will be a smaller parallax. So let's do that instead. So we'll do RI index the same way. So that's still columns 2 and 3. I'm going to get rid of that. Oh, no, you know what? No, I don't have to do that. Don't have to really change much of anything, except I need to change this to column 4, right? 1, 2, 3, 4. And we're not going to do a subtraction here because we'll do that. So I think that's about it. Let's multiply it by 0.15 again. That might be a little bit big, but let's see. So the positions of these aren't going to change, but the size of the dots are all going to change now, depending on more or less how far away they are. So let's see. Okay, that didn't work the way I wanted it to. Oh, it's not number 7, it's number 4. All right, 1, 2, 3, 4. There we go. Okay, that's kind of interesting. Let's, oh, it didn't like a few of those. 1, 2, 3, 4 times 15. Let's go 25. Here we go. So now what this is showing is the larger the dot, the closer it is to us. So as you can see, this guy is bigger than this guy, which implies that it is closer. Now, some of these dots look all the same, and I'm not quite sure why. Should we let's take a look at this actual file and see if we can understand why. So here's the parallax here. We could just sort of, I'm just going to sort of scroll down and see if there's anything funny. Yeah, see, some of these, it's funny because some of these parallaxes are negative, which is kind of weird. Some of the parallaxes don't even exist. So that's probably why we're getting a couple of little warning messages there. Let's look at this in a different way. I was doing this actually before. Let's look at just the parallax, okay? Just the parallax. And I think that's, as you can see, I was doing this before, 14, 0 to 4, 7, 5, and 6. What was I doing here? I don't know. 5 and 6, 1, 2, 3, 4, 5, and 6. I was looking at proper motion there. Let's just look at parallax. Let's do this. We do this 0. Science on the fly here, following our noses. Here's 25. Don't think that's going to do what I want it to do. No, see, we're seeing, yeah, not quite. Let's do that. Let's see what that does. Okay. Yeah, so see, all these dots down here are actually below 0. So that's a little funky. So this axis now is just the star number, right? There's something like 770 or something stars in this list. So actually what we can do is we can just we can go 0 like that. So we don't even see those anymore. So as you can see, as this number gets larger and larger and larger, these dots are getting bigger and bigger and bigger. And here, as you can see, we're seeing 2 stars that are actually pretty close, you know, relatively close to us. This is the closest one to us, but this one is definitely a little further away. So now what we can do, let's actually do this. This is a pretty interesting plot, actually. Do we want to do that? Let's, yeah, that's okay. Let's, yeah, actually. Let's do that one. Okay, so now I've sort of switched back to magnitude. So the size of the dot is the brightness of the star. And since I grabbed this data in order of magnitude, the brightest stars are going to be at the beginning of the list, and it gets fainter as we move down the list. But this axis is actually the parallax, which is a measure of distance. So the larger this number, the closer the star is. And as you can see, the two brightest stars in this field of view are actually the two stars that are closest to us. And yes, indeed, our primary star is closer to us than the secondary star. So very, very cool. By a pretty substantial amount. Now, we'd be able to actually compute this if we wanted to. It's simple trigonometry. But, yeah, I was just sort of interested in seeing that. And I think it's kind of interesting. So, yeah, and Sorcerer X, this live stream exists just to share a passion. I'm not really motivated to teach you anything or communicate anything at all. I just want to share a passion. I've been doing astronomy my entire life, as long as I can remember, and so I just have a passion, and I just like to share that. Now, you will learn things, and I definitely will communicate things, but that isn't really the motivation for this live stream. As I said, my motivation is just to share the passion. I'm almost constantly thinking astronomical things, and so I'm like, hey, there is a medium on which I can share the passion, so I'm going to. So, and yeah, there are so many ways to visualize data. It's really incredible, and you can do some pretty interesting art with it too. In fact, just as an aside, I think we're pretty much done here. I found that extremely interesting that those two stars, which were thought to be close to one another, turns out that they are not. One's in front of the other one by a pretty substantial amount. So very, very cool. So yeah, I just thought that was neat. And what I like to do is I like to, when I hear about things, right? What I do, being an astronomer, I like to go to the source, right? I like to go and look at the data and convince myself, because you can hear all kinds of things, people talk, the media reports, you hear all kinds of things, and it is really, really cool, this day and age, that we have access to all this data, right? Just sitting here, right? We have access to petabytes of data, right? Just huge amounts, and it's extremely cool. So one of the things that I do and I like to share is those kinds of explorations where it's like, I heard about this thing. The components of Alberio weren't actually associated with one another. Let's go look at the data, right? And so that's exactly what we just did. And to be able to visualize that, that's where sort of the know-how comes about. But yeah, as Uncle Bill points out, I actually make art with scientific data. Like you can see this in the background here. That was made by using the positions of the 4 Galilean moons of Jupiter, and just, you know, putting a little bit of art to it, put some colors in there, and yeah, you know, come up with those kinds of interesting patterns. I know it's kind of hard to see, but yeah. So I thoroughly enjoy doing all those kinds of things. I think being able to visualize scientific data is kind of an interesting thing, and I actually go beyond that as well. I can turn this exact same data into sound, and I can actually make music with this. Music. With this as well, and you know, some of it's pretty interesting stuff. So yeah, there's just all kinds of things that can be done with scientific data of all kinds. It doesn't have to be astronomical. It can be anything. It can be anything. So cheers. Let me check the chat really quick. Make sure there's not too much mischief over there.
Hey, Cosmic, I just want to let y'all know that tomorrow I won't be here. I'm gonna do another viewing party for WWE pay-per-view.
Oh, very cool. Very cool. All right. Well, you will be missed, but I'm sure you'll be back. So I'll definitely send you the link anyway. But yeah, very cool. By the way, that reminds me that every single Monday at 0 hours UTC, I show a Monday midnight movie over on my Rabbit room, and let's see if I can put a link up over here. Where did my there it is. I'll throw a link into the chat over here. So if anybody hasn't joined the Monday midnight movie yet,
it's Whiskey Echo, Uncle Bill. Whiskey Echo.
WWE. Yeah. WWE. Okay, cool. Yeah, Bobby's into WWE. That's pretty far out. Very cool. It's nice to have a lot of interests, you know. Okay, so what I guess where I want to go now is sort of back to the constellation of Libra. And if nothing else, I want to take a look at that globular cluster that was over there. And so I guess the thing to do is I'm going to share my screen again. And we'll go over, let's see, we'll go, we looked at Delta Librae. Let's go, I don't remember what NGC number it was, so I'm going to have to go all the way back over here. NGC 5897. So new general catalog 5897 globular cluster. So let's just you know, we'll sort of make that the object of the day, and we'll look at that. It was 5897, wasn't it? Yeah, 5897. So this is Simbad, which is a fantastic astronomical database. You can find out pretty much everything about anything over here. Oh, what? No. No. Not fair. Wow. Let me try to reload this. Oh, no. Oh, no. Sinbad is down. Down for the count. Well, let's see if HST looked at it, the Hubble Space Telescope, and maybe we can just play with the pictures here. So what was it again? 5897. Now it's very unlikely that HST has looked at this, but we'll try anyway. See if there's anything there. Okay, here's hoping. Oh, yay, there are some. So I'm going to sort this by date here. And yeah, it looks like they looked at this in a few different wavelengths. So here's one observer, right? So we can actually click on this proposal ID and get sort of a rough idea as to what they were using the HST for, right? All the observers, they have to make a proposal. They have to ask for telescope time, and then they have to make a case, right? They have to say, okay, well, this is why we think that we should get this extremely wanted telescope time with the Hubble Space Telescope. Let's see. So this is an ultraviolet initiative proposal to complement the existing. These are just different filters, globular cluster, treasury. So yeah, it looks like they just want to look at globular clusters with the ultraviolet, right? Which you can only do from space, right? You can't really see in the ultraviolet down here on Earth. So let's see, sensitive to carbon, nitrogen, oxygen abundance, variations, combination of these passbands with the optical ones also gives the best leverage for measuring helium enrichment. On and on and on. So yeah, pretty cool. So they obviously got a substantial amount of time. Here's the exposure time here in seconds, right, for each of these things. And it looks like they looked at these guys. Let's see, 336 was a 350, 336. So yeah, it looks like all the 336 nanometer filters had like a 350-second exposure. The 275s, they sort of varied, right? 1748, 1750, 1852. And then the 438, they did sort of some short exposures. So let's take a look here, and if these look pretty decent, we should put them into GIMP and colorize them and just sort of see what they look like with some false color, right? Because obviously in the ultraviolet, that they really don't have a color, but we can assign a color to each of these. So let's take a look. So it's a pretty loose globular cluster. I think we're sort of looking at the whole thing there. That's not incredibly dense or anything, but that's what we're working with. So there's a lot of cosmic rays and a lot of, you know, funky things here.
I just tried searching Wikipedia or to do a Google image search to verify it.
Yeah, I think this guy here sort of, you know, I'm looking at that, and yeah, you know, they're probably looking right in the middle here. So yeah, we're probably just seeing, you know, the central portion. So that's probably about right. So let's save this. Let's save this, and let's see, let's go up here, and then we'll go let's go here. Let's make a new thing called HST, and then we'll make a new thing called NGC. And I always, what is this thing called again? 5987. Oh man, I forget now. Well, we're gonna have to cancel it because I'm not gonna remember what that's called. 5897. Okay. I'm starting to get really old. Can't remember anything. 5897. NGC 5897. So,
You're creating a folder.
what's that?
Yeah, you was creating a folder.
Yeah. 301. Okay, so we'll call that number 1. And then, so that was 336 nanometers, and specifically 3,354.9 angstroms. So let's grab this one, which is at 2707. Should be the same field of view. Kind of interesting, slightly different looking. So we'll grab that one and we'll make that number 2. And then 438, right? 438, let's see, 140 seconds, 138 seconds, doesn't really matter. Let's grab this one. Okay, and we'll save that one as number 3. Okay, cool. So now let's go over here and go to HST 5897. So there they all are. Let's so I'm going to start up GIMP here. I'll just load up the first one with GIMP. X that out. Okay, so there's the first one. So now I'm going to load up the other ones. Number 2 and number 3. Open as layers. So now we've got 1, 2, and 3. All right, 1, 2, and 3. So let's go back over here. So the first one was at 336. The second one was at 275, and the third one was at 438. So, of course, this is all ultraviolet, but 438 is the longest wavelength one. So let's make that one red. So that's the third one. So let's make number 3 red. Oh, let's do this first. Make this a little bit bigger. That. Go into RGB mode. Oh, and I'm going to invert all of these. Invert them all. Okay, so now let's make number 3 red. And the other thing that I want to do was I want to do that, and I want to do that, and I want to do that. And you know, actually before I, all right, hold on, let me back up. We do this first. Screen. This screen mode just sort of adds them all up. It makes them all transparent. And the reason why I'm doing that first is because I want to make sure, at least sort of hope, that everything is lined up. And it's kind of hard to tell. Kind of hard to tell if these are lined up or not. Yeah, I don't know if I can tell. I'm just sort of blinking these on and off to see if I can see if stars are lining up with one another or not. It's kind of hard to tell. It looks like these strips, though, are all lined up. So I'm sort of thinking that maybe we're in good shape here. Kind of hard to tell. There's a lot of noise in these images, obviously. See now, yeah, here's two stars here that, nope, that's in the same image. So, okay. Yeah, all right, well, we'll go with that, see what happens here. So let's go all the way back, all the way back to that. Okay, so let's make this guy red. And so that was the 438 one. 336, let's make that one blue or green, right? Because that is right in between 275 and 438. So let's make number one green. Number one is going to be green. And let's make this one blue. So we'll just do the regular red, green, and blue kind of thing here. And I'm not sure if those are lining up really well or not. It's almost hard to tell because it's pretty noisy. I mean, it's very colorful, but yeah, it's a little hard to tell. So there's the blue one. See, there's a blue star here, a blue star here. Oh, there's a red star. Okay, is there a blue star up here? Oh, I don't see a blue star there. Blue and blue. Let's get out of this weird strip here. So these, it looks like a lot of this is noise, but these guys here look like stars, right? They're sort of extended. So, but wow, it's just not, I don't know if these are lining up or not. Not having good success with this one, and that's just really noisy. This is pretty raw data, as you can see, and now I'm just trying to make up excuses. Because yeah, I'm not seeing anything matching up. I'm not really seeing anything match up. So here's maybe some green stars here, but I'm not I'm not seeing anything in the blue like that. Oh, maybe here. This one and these two. Maybe. Maybe. I'm going to try to move these two green stars. Let me try to zoom in on those a little bit. So this is sort of the painstaking thing that astronomers have to do, right? So you're just seeing it live and for real here. I'm seeing, let's zoom in a little bit more here. Right, I'm seeing these two greens and these two blues, and they look pretty much the same distance apart. Oh, look, here's two greens and here's two blues. Yeah, I'll bet you that's it. Okay, so let's take the green stars and we'll move them so they overlap the blue stars. Okay. So just taking the green ones, scooching them down, scooching them over. Ah, I'm seeing things lining up. You see here? These two, these. Aha. I think we got it. Okay. So I'm going to make those go right on top of one another. Okay. Now we got to sort of do the same thing for the red. So let's look at the red and see if we can see any patterns. Ooh, I'm seeing it right here. Look at, here's these two reds and these blues. Maybe. Let's see. If that's true, then this one would go over here, right? These two, I'm not, that might be just a little bit out of the field. Let's, I really want to confirm this before I start moving. These two and these two could be. Well, let's try it. So let's move the, let's put these two reds on top of these two blues and see what that does. So I'm going to move the reds over. Methinks we got it. Oh, maybe not. Oh, maybe. Oh, I think maybe. A lot of these are stacking up okay. Oh, yeah. Oh, yeah. That's it. Okay, so now let's add the green in there again. And, look at that. We're seeing white stars. That's a good sign. So now let's back out a little bit. And, yeah, it's going to look really funky because these frames are all over the place. So that is definitely not the prettiest picture I've ever seen of a globular cluster. But I think I've got the alignment right. It's just that it's a very, very loose cluster, and the telescope obviously wasn't pointing exactly in the same place each time. So yeah, that's pretty cruddy. Definitely not prettiest looking thing I've ever seen, for sure. But I think I've got the alignment of the stars right, at least. But yeah, there's a lot of noise, and we could spend a little bit of time playing with this and printing it up, getting rid of a lot of the noise and stuff. But I think for now, I'm just going to save this as it is, and maybe I'll play with it offline a little bit. So, you know, this is the work. This is a little bit of the work, you know, that astronomers do. It's tedious, it's painful, but if you want results, this is what you have to do. And this is the data that we actually have to work with, right? And sometimes it's a mess, right? It's a total mess. And what I can try to do, it's really quick. Let me merge these into one and come up here and just see if I can play with the is it levels? No, it's curves, I think. Let's just see if we can play with this at all. Yeah, that's not really helping with the noise much. Maybe even making it a little worse. But you're starting to see the stars popping out there a little bit more. But yeah, pretty messy. Pretty messy. This would take a little bit more time to really clean up. But that's how data is. As I said, sometimes it's a mess. Sometimes it's a mess. So, all right, let's really quick, let's check Simbad again and see if Simbad has come back. Oh, no, it hasn't. Well, that sort of sucks. Simbad is sort of our go-to for all kinds of interesting astronomical data, but it looks like it is down due to maintenance downtime. So, that sort of sucks. Oh well. Let me, well, you know, maybe this is a good time to stop. It looks like it's just after the hour, and I try to be mindful of everybody's time. So yeah, very cool. I think well, hey Daniel, nice to see you. Yeah, Simbad is very rarely down. So you know, most likely, you know, they waited until, you know, we wanted to use it, and it's like, you know, let's just mess with them tonight. We'll, you know, turn it off for a little while. Probably, you know, in a couple minutes it'll come back on, and the live stream will be all done by then. But yeah, that's how it goes. You know, we're pretty casual and cool here. So, you know, if things don't go exactly right, that's one of the cool things about having a daily live stream, right? Is that we can always try tomorrow or the next day or next week, whatever else. So, okay, well, very cool. I think, Andy, I see you in the chat too. Nice. Thanks for coming in. But yeah, I think I'm going to exit this planet for now. So take care, everybody. Have a great evening, a great day tomorrow. If you're watching this later and not live, make sure to subscribe, smash the thumbs up if you so desire, and share this around. This is I guess, you know, sort of a typical live stream. You know, we just sort of follow our noses here a little bit, and you know, just have a good time thinking all things astronomical. You know, we mess with data, mess with images. This is for everyone. So whether you know a lot or not, doesn't matter. You'll hopefully always get, you know, something out of it. And some days are better than others. So yeah, that's just how it goes. But like I said, you know, this is just a casual, fun thing that, yeah, is just following the passion. So, all right, well, take care, everybody. I will see you again tomorrow. Now, this Earth continues to spin, right? And on the equator, it's spinning at about 1,000 miles an hour, right? So, I mean, we are really spinning fast, but it's so smooth and we're so used to it that we can't feel a thing, right? So, so hold on to your hats, right? But yeah, in one more spin of this planet, a little less than one more spin, we'll be back here at 2 hours UTC, and we'll do more astronomy. And who knows? Who knows? There's so much to talk about that I mean, I will never ever run out of things, because I mean, the universe is full of just absolutely amazing, inspiring, awesome things. And one of the things that I think we're here for is just to sit back and enjoy it, and just be in awe. So, all right, I'm going to get out of here for now. Peace, cheers, and all that. And I will see you all a little less than 23 hours from now. So take care, everybody. Bye.
Reminder that I won't be here tomorrow as well.
Okay. Sounds good, Bobby. We'll miss you, but we'll pick you up later for sure. All right. Bye, everybody.